in that world of Django, in that world of static web pages being served, Python was right at home. It didn't matter what libraries or runtimes the user had installed. All the code ran on the server in an environment that the developer controlled. Python was a language that let you develop your ideas quickly, and the end client didn't need Python at all. They just needed a browser. But over the last 14 years, the web has changed quite a bit. What started as a little bit of JavaScript has now grown significantly, and we're now in a situation where by lines of code, the amount of code needed by your front end can often compete with the amount of code needed by your back end. But even though we're seeing more and more logic on the front end, we still need logic on the back end. Consider something like form validation logic. If you want to make a user interface responsive, you do that on the client. Now, nobody likes duplication of logic. So if we're going to avoid that duplication, we have a problem. The browser only supports one language, and that language is JavaScript. So what are we going to do? Well, one option is to abandon any language other than JavaScript and use JavaScript everywhere. That line of thinking is what brought us Node.js, and plenty of people have certainly written plenty of applications with Node. But this approach deeply concerns me. Polylingualism, speaking many languages, be it human languages or computer languages, is a good thing. In my 30-odd years of programming, I've seen nothing to lead me to believe that that isn't true of programming languages as well. Learning a second or third or fourth programming language, especially when it uses a different programming paradigm, is a great way to encourage your brain to think about problems in different creative ways. Every programming language is slightly different, and the ecosystems around those languages are different. The proposition that all programming should be done in JavaScript is, to my mind, the very definition of if all you have is a hammer, everything looks like a nail. And the idea that JavaScript should be that single language everyone uses simply because it had the good fortune to be the only language Netscape supported in a browser 25 years ago, that's absurd. Now, don't get me wrong, there are talented people in the JavaScript world and good resources in that community. This isn't a critique of the specific strengths and flaws of JavaScript as a language. Any grand vision of the future that is based upon a language monoculture is, to my mind, a folly. Or at the core of all good engineering is picking the right tool for the job, and a language monoculture is an artificial constraint on the tools at your disposal. Interestingly, it wasn't always this way. When Netscape introduced the browser, they introduced this new language, JavaScript. But Netscape was just one player in this new web space, and other players had other ideas. In the mid-90s, Microsoft was everything, and Microsoft's scripting language of choice was Visual Basic. So early versions of Internet Explorer would allow you to script your web pages with VBScript. Now, I say early versions, this was valid until quite recently. It wasn't deprecated until IE 11 in late 2013. Python also had a play in this space. Up until 1999, Guido van Rossum was working at CNRI on an academic project looking at electronic knowledge storage and retrieval. And part of that project was a custom web browser called Grail, a web browser written in Python. And you could embed Python into your web pages. And thus you had Python in the browser, or at least Python in a browser, because Grail was the only browser where this actually worked. But these alternatives were short-lived. By the time the browser wars came to a conclusion in the early 2000s, JavaScript was really the only language that any browser supported. Google made an attempt to introduce Dart as a new language, but that really wasn't all that successful. So in reality, if you want to use a different language in the browser, you're going to have to get creative. To demonstrate, let's try to do something practical. Let's validate some credit card numbers. Now, all the code for these examples can be found on this webpage, the bit.ly link there, which is also a live demo of all the code running. For those who don't know, credit card numbers are self-validating. They contain a checksum. The last digit is computed from all the previous digits following a method known as the Luhn algorithm. And using this algorithm, you can't tell if your user has sufficient funds, but it will protect you against simple typos and other sort of credit card validity checks. And it's a great example of logic you want to run in the browser because you want to give the user immediate feedback if they've made an error fat-fingering their credit card number. Now, if you were writing a native JavaScript version of the Luhn algorithm and connected it up to a form, you end up with about 30 lines of code, about 0.6 kilobytes of native JavaScript. You minify that, it goes down to about 0.4 kilobytes. But what if you don't want to write JavaScript? What options do you have? Well, the first option is to write JavaScript, but to use a different syntax, compile to JavaScript as a pre-compilation step. This is called transcompilation. Coffeescript is probably the most popular version of this in practice. Coffeescript is, at its core, JavaScript with different spelling. It's got a few nice pieces of syntactic sugar that map nicely onto JavaScript, and of course, syntax significant whitespace in place of parentheses. And if you write your Luhn algorithm in Coffeescript and compile it to JavaScript, there is a little bit of overhead. The for loop is a little bit odd. Coffeescript syntax itself is more terse than JavaScript, but in compilation, the output JavaScript is a bit more verbose. The compiled Coffeescript has increased our payload by about 30% to about 0.8 kilobytes, but it's only 10% once you minify it, about half a kilobyte total. Okay, that's Coffeescript though. Can we use this technique for other languages? Say another language that has syntax significant whitespace, for example, like Python. Well, sure you can. And there are a bunch of projects that try to do this. The best one that I found is called Transcrypt. So we can write our Luhn algorithm in Python, and because it's Python, we can use list comprehensions and enumerate and actual integer arithmetic. We then compile our Python source file, and again, we get JavaScript. Now, this is just a small segment of the code that is generated, and right away you'll see this is definitely not JavaScript that you would write by hand. Why is it so weird? Well, some of it is because of language idiom. JavaScript's loops, for example, for loops, for example, are C-style for loops. They have a start, an end, and an increment. Python uses for-item initerable. But beyond that, it's because we don't just want a language that looks like Python. We want it to behave like Python as well. And Python's scoping rules, the rules of where variables are accessible, are quite different to JavaScript's scoping rules. If you want to preserve Python semantics in JavaScript, you can't just do a naive syntax conversion. That part's easy. It's why compiled Coffeescript still looks mostly like JavaScript. It has the same scoping rules. There's no translation needed. But for Python, you actually have to parse the code and generate JavaScript constructs that expose the same lexical scoping as Python expects. You also have to account for language built-ins like enumerate and sum. Python has a lot of batteries included that JavaScript doesn't have, and you've got to provide them. If you were aggressive, you could probably shake the source tree and strip those out, but that's not a feature that Transcrypt provides out of the box. And so the final compiled Transcrypt product for this example is 74 kilobytes of code, about 32 kilobytes when minified. Most of that extra weight is a fixed cost associated with providing built-ins. The actual Python Luhn algorithm part is only 1.5 kilobytes, about double the size of the raw JavaScript. Now that's a lot more payload, a lot more code to send, but you are now running Python in the browser. You're not running all of Python. You get the language, you get the built-ins. You can even access the DOM. Window, document, other DOM objects are exposed as global symbols in the Python namespace. You can manipulate your HTML page to your heart's content with Python. Transcrypt provides source maps as well, so you can debug Python code in the JavaScript debugger of your browser. However, you don't get a REPL, a read eval print loop, otherwise known as the Python prompt, or at least not the Python one. You are ultimately running JavaScript code, not Python code. So there's no drop to the prompt to run Python. You can drop to a prompt, sure, but it's the JavaScript prompt where you're running JavaScript, not Python. You also don't get the standard library. You can't pip install requests and start doing client-side web requests. Transcrypt does include partial support for NumPy, but that is a very specific inclusion that the Transcrypt includes. Okay, so transpilation proves it's possible to compile to JavaScript from a source language other than JavaScript. So let's think outside the box. A Python compiler is just code. Can we write a Python compiler in JavaScript? If we had that, then we could actually ship Python source code to the browser, much like VBScript used to, but without needing any formal support for our language in the browser. Well, yes, we can do that. Brython and Sculpt are both implementations of the Python compiler written in JavaScript. And if you have a browser-side compiler, that means you can ship Python source to the client. So you include the code of your compiler as JavaScript source, and then you include the Python source code in a script tag. That script tag can then import other code. Brython's import statement will download Python files from other URLs. You can also reference the DOM. Brython does this with a module import rather than putting symbols in the global namespace. When the page loads, the Brython source code looks for script tags of type text Python, compiles them, and runs them. Now, I'm showing the procedure here for Brython. It's very similar for Sculpt. Awesome, we've got Python in the browser. What's the catch? Well, what's the code size like? The Python code's about 0.5 kilobyte, smaller than the original JavaScript. But you need a 646 kilobyte bootstrap. And that bootstrap has to be fully downloaded, parsed, and executed before any of the Python source on the page executes. And it's very noticeable. I've got a 50 megabit connection here. If I visit the Brython webpage, they have an amazing clock demo on their front page written in Python. But that demo isn't visible at all for 2 to 3 seconds after the page is finished loading, because the demo code won't run until the bootstrap is finished loading and it's fully parsed and compiled your source code and run the source code on the page. What else is missing? Well, again, you get all the DOM, all the Python language built-ins. You get some of the standard library, but it is missing parts. You also don't get any debugging. Brython doesn't provide source maps and may not actually be able to, because you're not mapping from one source file to a roughly equivalent JavaScript source file. You're mapping from the internals of an interpreter to source code. Brython does have a debugging mode, but it's not connected to the JavaScript debugger that you might be familiar with. You do get a full REPL though. You've got a full Python interpreter at your disposal. You can't just open up the JavaScript console and start typing, but you can, with relatively little effort, add a debugging console to your web page that accesses a running Brython interpreter. But after that, you've still got a 650 kilobyte bootstrap. How much of that can we strip away and still have a working project? Well, it turns out quite a bit, because what you're shipping to the browser is a full Python implementation. What do I mean by that? Well, a full Python implementation consists of a parser, which takes human input, turns it into an in-memory representation of code, a compiler, which takes that in-memory representation and turns it into something that can be executed in CPython, that's bytecode. There's an eval loop, which can read and run the output of the compiler. That's what you experience as the Python executable. And then there's the standard library, which is used by the code running through the eval loop. Now, the approach taken by Brython and Sculpt is to re-implement the whole thing, rewrite the whole lot in JavaScript. But all we need to be able to do is run the code. So if we ship a runnable version of the code, we don't need to ship a parser and a compiler. And Python has a runnable representation. It's called bytecode. That's what you find in PYC files. Bytecode is a bit like high-level assembly code. It's an encoded set of instructions for a stack-based virtual machine that has basic primitives like pushing and popping on a stack, setting attributes on an object, handling exceptions, and so on. Bytecode is a runtime format used by the CPython interpreter. But there's nothing to say we couldn't create an independent implementation of the CPython virtual machine capable of running CPython bytecode. And that's what Batavia does. Batavia is an implementation of the CPython virtual machine written in JavaScript. What does it look like to an end user? Well, instead of shipping source code, you ship the PYC file, base64 encoded here, so it doesn't cause any binary encoding problems. And how much code are we talking about? Well, the bytecode is about 1.2 kilobytes of base64 payload for our Luhn example. It's also mildly obfuscated, which, depending upon your perspective, might be a good or bad thing. But just as with Brython, there's a bootstrap. Unfortunately, the current state of Batavia doesn't look too good here for a bunch of reasons related to badly managed complexity. Batavia's bootstrap currently weighs in at about 5 megabytes. However, once upon a time, Batavia's bootstrap was as small as 10 kilobytes of minified JavaScript. And if you don't believe that's possible, Ned Batchelder's ByteRun project is a full Python bytecode machine written in 1,600 lines of Python. Alison Kapter did a great write-up of that code in the book, The Architecture of Open Source, which I highly recommend if you haven't read it. So if we leave behind the ability or the need to compile code, you can lose a lot of what makes Brython heavy, weight that Brython can't shed, because client-side compilation is how Brython works. So the current state of Batavia isn't especially competitive, but I think there's an underlying idea there that's viable. The implementation just needs some work. We'll come back to that. Assuming we can address that size problem, though, what would you get? Well, you get the DOM, you could get the built-ins, you get as much of the standard library as you care to ship, but you wouldn't get any REPL or debugging. You'd essentially get the same story as Brython, but without the REPL. So let's think outside the box again. This is a line of thought that's worth exploring. What Batavia is doing is essentially shipping code that targets a runtime. Batavia then provides the runtime, reproducing CPython's runtime in JavaScript. But JavaScript is itself a runtime. So can we target that runtime directly? One of the side effects of having multiple competing browser vendors is that over the years, they've competed with each other to make the fastest JavaScript interpreter. Thousands of person-hours have been put into making JavaScript run fast. And a lot of that effort was put into just-in-time compilation, or JITting. JITting is a compiler technique that identifies pieces of code that run fast and turns them directly into machine code at runtime. A few years ago, a team at Mozilla looked at the JavaScript language as a whole and worked out the subset of the language that jittered efficiently. Now, in theory, if you only use that subset of JavaScript, your end code will run really fast. They called this subset asm.js. Why? Because it's effectively assembly-level JavaScript. It's a set of very low-level primitives for dealing with integer, floating point arithmetic, function definitions, function pointers, things like that. Now, here's some asm.js JavaScript for adding two numbers. We define a JavaScript function, and the first thing we do is we OR the value of the first argument with 0. Now, logically, that means nothing. Any value ORed with 0 is the same value. But a compiler can then infer that first must be an integer, because the result of a binary operation with an integer is an integer. And so any subsequent operation on first must be an integer operation. We don't need to do the operation where the compiler can determine just in time that it doesn't need to do anything other than integer operations and just do that optimized calculation. Now, nobody seriously expects anyone to manually write JavaScript like this, but rigorous mechanical application of rules and logic is something that a computer is really good at doing. And so people have built compilers to do it. Now, although Clang is usually thought of as a C compiler, it's really a toolkit for building compilers, parsing human readable source, building an intermediate representation that encompasses the underlying instructions that need to be performed, with backends to turn an intermediate representation into output for specific CPU architectures. But asm.js is also a way to perform those machine level instructions. So you can write a compiler backend that outputs asm.js directly. And Scripton is that backend. If you've got a language that Clang can compile, and there's a lot of them, it can output asm.js output. And if we rewrite our credit card validation function in C, we compile it within Scripton, we get something that looks a little bit like this. A whole lot of completely alien, but 100% legal JavaScript code that will, at runtime, be very, very fast in a JavaScript virtual machine. Now, it's not just a magical fountain of speed. There is a price to be paid. You don't get a transparent bridge between JavaScript and native code. Integers and floats can be passed back and forth relatively easily, but strings, they have to be marshaled because asm.js is assembler level code. You have to manage memory yourself. You have to allocate memory on a virtual memory heap, fill it with bytes, and then point the asm.js code at that virtual memory address. And Scripton provides a bootstrap to help with this, but it's pretty low level. You can see in this code sample, there's a module.ccall method, which is used to call a C function in your Scripton module. And you have to manually declare the types of all the arguments so that the bootstrap can then allocate memory for the string argument that we're going to pass in. What you do get, however, is access to raw canvas and OpenGL 3D graphics APIs. So for example, if you head to quakejs.com, you can find a full port of Quake 3 compiled and running in your browser. It takes a minute or two to download, but once it's there, it is a fully functioning 3D first-person shooter in your browser. Why does this work? Because Quake is written in C using OpenGL and keyboard inputs, so it can be compiled directly to target the web. So, our Luhn example can be written in C, compiled to asm.js, and if you do this, you get about 194 kilobyte of asm.js code. If you turn on compiler optimizations, that reduces down to about 32 kilobytes, including a bootstrap. But even asm.js can be improved upon. What is delivered by asm.js is still JavaScript code, which needs to be transmitted in a text format, then parsed, then interpreted, and then jittered. If we know ahead of time that our code will be compatible with this fast JavaScript subset, can we send it to the browser in a ready-to-use quickly format? We can, and that's what WASM is, or WebAssembly. WebAssembly is a binary format formalizing the asm.js language subset into a format that can be delivered to the browser in a pre-parsed, pre-jittered format. That makes it smaller and faster than assembly.js, even though fundamentally it is the same code that's going to be executed. Now, there is a source code format for WebAssembly called WAT, for WebAssembly text, sort of a hybrid between Lisp and assembly language. This really just gives formal names to the individual asm.js operations rather than relying on compiler tricks. The WAT file can be compiled to WASM, which is a pure binary format. That means it's plausible to handwrite WAT if you want to and compile it to WASM, But WAT also is also supported by Nscripton and some other compilers. So you can take C code, run it through Nscripton with a different set of flags, and you get WASM output that is smaller and will run faster than the asm.js output. And what you get is 22 kilobytes of binary WASM plus 100 kilobytes of Bootstrap, which reduces to 0.3 kilobytes plus Bootstrap, 18 kilobytes of Bootstrap, if you turn on compiler optimizations. The capabilities of WASM are identical to asm.js. It's just smaller and faster because of what it's not doing. And excluding Bootstrap, the code for the Luhn algorithm is smaller than the original minified JavaScript implementation. Now, this isn't a theoretical future thing either. WASM is supported in all the major browsers in use today. If your problem suits WASM's capabilities, you can use it right now. Now, okay, we did have to rewrite our Luhn algorithm in C to use Nscripton, so that doesn't help us run Python, but the CPython interpreter is written in C, and if we can use Nscripton to compile any C, can we compile CPython? Why, of course we can, and that's what Pyodide is. Pyodide is CPython compiled for the browser, and it's a bridge between Python and JavaScript. Is a little bit odd. What you end up doing is running a script, where the script is a string. You pass in any JavaScript arguments as strings to the script that's going to run, and the last expression in the Python code is the return value of the Pyodide call. Now, this is at least partially because the developer's primary use case for Pyodide is essentially a Jupyter-style notebook that runs completely in the browser with no server-side support. And in that context, all you really want to do is run chunks of code that the user provides in a Python virtual machine. The downside is that it's not small, and at least at the moment, there's a lot of caveats. What you get is effectively a full embedded CPython in the browser. Great for running Python shell in the browser demos or Jupyter notebook session type things, but not really great for embedding web application logic. There's no DOM, there's no browser debugging, and while you do get the parts of the standard library that are written in C, you don't get anything of the interesting parts of the C standard library, like sockets, for example. And it is big as a result. The WASM file for Pyodide is almost 3 megabytes plus 6K of minified bootstrapping, and that's before you've given it any Python code to run. Now, there's two reasons it's so large. The first is that, just like Brython, it's a full Python runtime, not just the bytecode interpreter. And the second is that it includes, compiled in by default, a lot of extras, including lots of numerical processing tools, which is fine for a computational notebook setup. You download the page once, wait a couple of seconds, keep the page open. But when you're having to deliver all that payload to the client on every load of a web page, it's overhead you probably don't need. The good news is that there is lots of room to optimize here. One obvious optimization is to use a smaller Python. MicroPython is a Python interpreter written for embedded devices like the Adafruit embedded devices, and it's written in C. And an Nscripton compiled version of MicroPython is actually available on the Node package manager today. Now, that's an interesting avenue, but it still exposes a full Python REPL in the browser. Perhaps the best way to optimize here is to take on the Batavia approach, to strip back the Python interpreter to just the runtime and get that in WASM format. If we get that, that may be the easiest way to get a small and fast Python in the browser. Now, I have been focusing on Python, but none of these techniques are especially Python specific. I like Python a lot, but I don't want Python to become a monoculture any more than I want JavaScript to be one. There are countless other languages that have analogs to the techniques that I've described here today. But the thing is, WASM is a binary format. When you use a Unix.so binary library, you don't care what language the library was written in. You just link against it. Multiple languages can coexist in a single executable. WASM brings the same capabilities to the web. It doesn't care what language was used to produce your WASM binary. It just exposes an interface that can be invoked by other WASM code. The future of a web that isn't focused on JavaScript is starting to look really promising. In the mid-90s, Java was the hotness because it was going to deliver write once, run anywhere code. And it was able to do that because it specified a bytecode format and provided a cross-platform virtual machine. But it strongly coupled that runtime to a new programming language, Java. And while the world got really enthusiastic about Java, and Java isn't going anywhere anytime soon, Java has not completely replaced all other programming languages, nor will it ever do so. JavaScript was invented at about the same time, and it's called JavaScript, not because it had anything to do with Java, but for marketing purposes, to capitalize on all that cross-platform enterprise-ready computing buzz that mid-90s Java had developed. JavaScript was a new language. It was cross-platform too, so by golly, it had to have Java in its name. JavaScript didn't have a standardized bytecode format or provide a virtual machine to make it cross-platform. It only worked in the browser. But over time, the web has become so important as a platform that people have tried to bring JavaScript everywhere. They've tried to reinvent the universe using only JavaScript, making exactly the same mistake that Java made, focusing on the language and not the runtime. The great irony in all this is that the promise that Java originally made, write once, run everywhere, that promise may end up being delivered by JavaScript, a language that borrowed the Java name purely for marketing purposes. But even then, we're going to get the capability by ignoring JavaScript, the language, entirely. JavaScript has the potential to be an actual universal computing platform, not because of JavaScript, the language, but because of the importance of the web as a platform and all the effort that's been put into optimizing JavaScript runtimes as a result. Almost by accident, we have ended up with WASM, a mechanism for describing cross-platform native executables. And that is ultimately better for everyone because it abandons the idea that there is one programming language to rule them all and lets every language find its own niche and lets different languages, including Python, coexist and cooperate in that ecosystem. But even more importantly, the stage has been set for the next web revolution, a new generation of web frameworks that actually use this capability. We have, for the last 10 years, seen the web change from being a server-driven document generation interface to an application platform. However, our tooling really hasn't kept up with that shift. Today's best client-side frameworks really do still treat the web as a dynamic document generation platform. In the mid-80s, PCs gained graphical displays, and every application developed its own GUI from scratch using bitmap display primitives. Some were good, some were bad, but there was a huge amount of duplicated effort and no consistency of experience. Then Windows 3.1 came out, and instead of everyone developing GUIs from scratch, you just used the primitives that Windows provided, buttons, windows, dialog boxes, inputs, and so on. Even bad GUIs met basic standards because there were shared resources. Right now, most web developers view web development as a matter of manipulating primitives, but rather than manipulating bitmaps, we're manipulating markup and CSS. And some web GUIs are good, a lot of them are bad, because there's so much reinventing the wheel of basic UI metaphors going on. In my view, the web is ripe for a Windows 3.1 style revolution to start providing high-level APIs to describe rich application interfaces, describe UI metaphors like dialogues and menus, to build frameworks that treat the web as an application delivery platform. And because it's WASM, there's no requirement these new frameworks be written in any particular language. The next web-changing framework could be written in Python. And because of WASM, it can be completely compatible with tools written in other languages. The last couple of years, the work I've been doing on this and related projects has been captured under the umbrella of the Beware project. Beware is my attempt to enable us to use Python anywhere that you might want to put business logic, on your phone, your tablet, your set-top box, in your browser. If you'd like to support the work that I'm doing in the Beware project, you can join the project as a financial member. You can also back me on GitHub sponsors. If you've got ideas or experience that might help an open source project fund its development, or you'd like to know more about the project, or you'd like to get involved, please get in touch, and I'll be hanging around for at least a couple more hours this evening. Thank you all very much.